so much for coming for the ES Research Talks. And this is our talk number 4. And today our guest speaker is Mehmood Hasan. He recently joined ES faculty in GIK. Uh, Mehmood's background is mathematics. He did bachelor's in mathematics and an MS from mathematics from University of Peshawar, and then MS from the UUT Peshawar as well, right? Before coming to GIK. And today's talk is about particle swarm optimization for active contour models and application to medical images. Please, Mehmood, you can come up.
Thank you so much, Dr. Muzarali, for introducing me. Thank you. So I start the talk with the name of Almighty Allah, the most gracious and the most merciful. So the title of the talk is Particle Swarm Optimization for Active Control Models and Application to Medical Images. These are the contents: introduction, existing model, proposed model, experimental results, conclusion, and at the end references. First, I would like to introduce some basic concepts of image processing. So we start with the very basic concept, which is digital image. So in mathematical point of view, mathematical digital image is just a two variable function whose domain is the set of all ordered pairs in the plane such that whose points are just shows the position of the pixels of the image, and the range of the two variable function gives us a scalar quantity that shows the intensity of the pixel at that point, yeah, the amount of color at that point. Next, image processing. It is just a technique to perform some operations on an image in order to extract some useful information from the data or from the image, like image denoising, image restoration, face recognition, and etc. Next, image segmentation, which is our topic. So segmentation is basically a section of image processing for the separation of information from the required target region of the image. You see here we have an input image, and the second one is we place contour on the object or on the image and apply some energy constraint or fitting terms, etc. to shrink or to expand the contour about the edges of the object in the image. You see in image C, the contour fulfill the edges of the object and segment the tumor or the object in the image. Next, active contour models. Basically, active contour are one of the active segmentation techniques that utilize the energy constraint and forces in the image of separation of the region of interest. Often we use two models. The first one is called edge-based models, and the second one is called region-based model. Edge-based model utilize image gradient to stop the evolving contour on the boundary of the tumor or the object in the image. But these models are sensitive to objects with weak boundaries. If we have an image and having the tumor, and the tumor has weak boundaries, this model would not very well result with us. So the second is region-based model. But region-based models utilize region information to control the active contour motion. And these models are sensitive to, not sensitive to the object with weak boundaries. And the third is these models are sensitive to inhomogeneity. Inhomogeneity means if the image contains a grayscale or the RGB image rather than the black and white images. The next is optimization technique, particle swarm optimization. Basically, this optimization technique is a population-based technique inspired by the social behavior of birds, flocks, or schooling fish. So PSO is initialized with a group of random particles. Each particle I has a position as well as a velocity at a given time step t. Additionally, the particle I possesses a memory of its own so far obtained best position called the personal best and denoted by P. And the best position ever attained by the whole swarm is called the global best and denoted by G. The position and the velocity of each particle is updated by equation 1 and equation 2. In equation 1, there are some parameters like omega. Omega is the inertia term. C1, C2 are the accelerating terms globally and personally. And R1 and R2 are random terms which lie 0 and 1 inclusive. This is the flow chart of particle swarm optimization. Next, existing model. LGDF model. Wang et al. Presented an active control model based on local Gaussian distribution fitting energy. It defines a local Gaussian distribution fitting energy by using local means and variances as variables. The energy functional of LGDF model can be defined as given in equation 3. Here we have 4 terms. The first term represents the fidelity terms, and the second term represents the length term, and the third and fourth term represent the fitting term of the energy functional. After that, if we minimize this energy functional by using of gradient descent method, we get this evolution curve that is partial phi or partial t. Just this partial differential equation gives the energy gives us to energy to movement the contour around the object. Here are some examples. Medical images results of LGDF model segmentation after 700 iteration, where first row contains the input images with different initial contours and second row represent the corresponding final contours. If you see here, the placement of the initial contour and different position, but the segmentation results could not well. This is the main drawback of LGDF model. Here we just focus on this issue. We have to find some initial contour that is best for all the medical images as an initial contour. So for this, we use another paper like the Whitehead proposed particle swarm contour search with the goal of finding the contour for a statistically homogeneous object in a search space. But this algorithm just only for the statistically homogeneous object. We modify this algorithm to an image having grayscale color. So algorithm 1 shows a pseudo code description of the initialization and overall structure of the algorithm. These are the examples of PSCS model, and now this is our proposed work. So in this section we explain our approach which makes LGDF model automatic and robust for their initialization. So for this we have used some pre-processing techniques which are as follows. The first step is our pre-PSCS processing. Here in image A we have an input RGB image. In second image we just convert this RGB image to a grayscale image. After that we remove the noise using the mean filter. So this image C represents the image after applying mean filter. Step number 2, we use particle swarm contour search. So after the first step, we then apply the PSCS-C algorithm 1. So this result shows PSCS-C algorithm. And next, step number 3, post PSCS PSCS processing, applying some morphological operations. So we get some dominant boundary points of the tumor. And these boundary, according to these boundary points, we find the center of the tumor as well as the radius of the contour. So result A is the PSCSE result, in image B the post PSCSE processing, and image C visual representation for center and radius calculation using the particles information. After step number 4, LGDF model for the final segmentation. So in this step we choose an initial contour as a circle using the information of the particles, and then apply the curved evolution of LGDF model for final segmentation, which is already defined in above section existing model. Here you can see first we have an original image. If the original image is RGB, convert it to a grayscale image, and then apply the pre-processing technique like applying mean filter. After that we get PSCSC result, and then post PSCSC processing, and then make a circular contour having the radius and center as well, and then initial contour. After that we apply the LGDF model, we get the final contour, and at the end segmented binary image. These are the pseudo code of our proposed model. So these are the experimental result. You can see here first the original image, second is the initial contour using our PSCSC algorithm, and third image represent the final contour, and fourth image represent the segmented image. So our proposed PSCSC LGDF model after 200 iteration. You see above, the LGDF model cannot achieve the result after 700 iteration, but here we can achieve 200 after 200 iteration. So now Jaccard and dice similarity coefficient, these are the measuring tools to measure our result, so the existing result. Like Jaccard shows the measure of one set to another set representing by the length of A union B divided by the length of A intersection B. So you can see here our Jaccard's similarity index is 0.9356 plus minus 0.0192, which is closer to 1. So if this value is closer to 1, our segmented result more accurate. If this result is approaches to 0, so our segmented result is not accurate. So the result achieved for GSC or dice similarity coefficient, the fourth column represents the number of iteration, and the fifth one is processing time. So conclusion, the mainstream techniques for segmentation suffer from the contour initialization, and most of the methods are working on manual initialization. So in this paper we propose novel level set models assisted by PSCSC to solve automated segmentation of medical images. So our proposed method is evaluated using medical images of cancerous skin, and the comparison with existing approach reveal that proposed technique outperform existing methods in performance and convenience for users. In the future, we will investigate recently emerged deep learning techniques for more precise segmentation. And these are the references. Thank you.
Thank you, Mehmood, for your brilliant presentation. The floor is open for question. You can ask anything from Mehmood.
Thank you so much, Mehmood, for such an elaborate sort of presentation. That was really a great insight of what you have done so far. So a couple of maybe queries regarding me, or maybe if I'm not able to get that point. You have used particle swarm optimization.
Yes.
Isn't it preferable to use ant colony optimization rather than this one?
Yes, we can use ant colony optimization, but you can see in ant colony optimization the particles are rather than a swarm, but they are in a straight line.
Okay.
So maybe it's not good enough.
Okay. So that's what I want you to convey. Like you have some sort of edges. You need to
Yes.
detect the edges. According to my knowledge, you were detecting some sort of tumor or cancer or something like that, maybe, if
Yes.
I'm not wrong. So for detecting the edges, for example, if you want to cure some sort of tumor or cancer, we need to locate it first of all.
Yes.
To locate it, we need to have some sort of edges, right?
Yes.
Can we use Harris edge detector or Harris corner detectors for these sort of things rather than going towards that rigorous mathematical
But their
representation?
models we use in just binary images. These are, you can say, grayscale images having more than having very much intensities, or you can say inhomogeneities.
Perfect. So the last question, I can continue. Like you mentioned number of iterations. So any idea for how to choose that iteration, or we can keep trying again and again and getting the exact result? If, for example, you got the result at
If
700.
here we plot some ground truth, that is existing segmented result. So if the similarity index achieves some tolerance, then the iteration stop over there.
Okay. And
Yes.
the software you have used? Which tool?
MATLAB and
MATLAB
Python.
and Python.
Yes.
Thank
Thank
you.
you.
Thank you so much.
Okay, Mehmood, thank you so much. I do have a question, and the question is probably in the context of medical images, right? Because you worked on it. Is there a requirement to have a 3D image of the tumor detection to understand the depth of how large the tumor is? Are there need for
This topic
development?
will be studied in image registration, not in image segmentation.
Okay.
In image segmentation, at first slide I defined the digital image. It is
Right.
a 2D,
Mhm.
two-dimensional function, or we can say two-variable function.
Mhm.
So we can discuss in a plane, so not in space.
But in a plane, you only construct the contour, right?
Yes, contour.
If I think about a 3D surface, then it will be interpolation of contours, right?
Obviously, it is a surface.
Right.
Obviously.
Okay. Um, all right. That's pretty much from my side. But I do have one more comment. Is that, for example, the model you have used, why not use maybe other optimization techniques other than particle swarm? Was it limited to the capacity that you don't have gradient information about the gradient?
Yes.
Yeah.
Particle swarm is just a stochastical model.
Right.
So it choose the points in the plane or in the
Mhm.
image, just and we can say randomly. So that's why.
Okay.
More question?
Okay. I guess nobody wants to ask anything, right? But please do ask question. That's what this session is about. And I would like to comment one more thing is that Mehmood is a perfect example, somebody working from a mathematics background and doing research in applied part, right? But in the applied part, your contribution, your novelty is still mathematics,
Yes.
right? And that's what we also wish to encourage in ES for people who are working on fundamental sciences that they should think about building a bridge toward application part too. So, Bas, thank you so much, Mehmood.
Welcome.
Yeah, right.